Hello everyone. Today I'll present our group project on anonymity and privacy protection in network communication on behalf of my team. First, let me introduce our team members. I'm Chang Liu, is responsible for background research and forensic detection analysis. Shushan Wei serving as the project coordinator. Zai Lu is our technical lead. Guli Zhang handles forensic analysis. The four of us completed this project together. In today's digital world, network anonymity technology is a double-edged sword. On one hand, it protects user privacy and freedom of speech. On the other hand, it can be exploited to conceal criminal activities, creating significant challenges for digital forensics. As VPNs and Tor become increasingly popular, forensic investigators must deeply understand how these technologies work and what traces they leave behind. Let me start by introducing our research background and objectives. Network anonymity technologies present a fundamental dilemma for how to maintain investigation effectiveness while protecting legitimate privacy. Traditional digital forensics assumes users leave permanent, retrievable traces on devices and networks. However, anonymity technologies are challenging this assumption. Our research has 5 core objectives. First, document baseline network characteristics without protection as a control reference. Second, evaluate VPN effectiveness in preventing IP and DNS leaks. Third, analyze Tor's anonymity strength and fingerprinting resistance. Fourth, identify forensic artifacts that remain despite anonymization. Fifth, provide practical guidance for privacy protection and forensic investigation. To achieve these goals, we designed 3 experiments: baseline, VPN, and Tor. We used Wireshark for traffic analysis, browser fingerprinting tests, and DNS leak detection. Before diving into the experimental results, let me briefly explain how VPN and Tor work. VPN architecture is relatively straightforward. It creates an encrypted tunnel between the user's device and the VPN server. All traffic passes through this tunnel to the VPN server, which then accesses the internet on behalf of the user. This masks the user's real IP address and encrypts data in transit. However, VPNs leave forensic traces such as virtual network adapters and connection logs, and may have DNS or WebRTC leaks if misconfigured. Tor architecture is more complex and secure. Tor uses multi-hop routing. Traffic first passes through an entry guard node, then a middle relay node, and finally exits through an exit node to reach the target website. Each layer is independently encrypted, like the layers of an onion. Critically, no single node knows both the source and destination addresses, providing extremely strong anonymity. However, Tor also leaves forensic traces including browser configuration files, registry entries, and connection patterns to known relay nodes. Now, let me invite Wei Shuxing to present the detailed experiments.
I will introduce our experiment A and experiment B in a simple way. In experiment A, we didn't use any tools like VPN or Tor. We just connected the internet normally and captured the network traffic. The result shows that our real IP address and DNS were fully visible. Also, the browser fingerprint was amongst 100% unique, which means websites could easily recognize us. Even though HTTPS encrypted the data, the SNI field still leaked information about which website we visited. So, the conclusion is, without any protection, there is almost no anonymity. Everything can be seen by others. Next, in experiment B, we connected to the internet through Proton VPN. This time, our IP address changed to a server in Romania, and all DNS queries was encrypted inside the VPN tunnel. There were no WebRTC leaks, which means our local IP was also protected. However, the browser fingerprint stayed the same. It was still very easy to track us. This shows that VPN mainly protects the network level identity, but not the device level identity. Compared with experiment A, the VPN greatly improved our privacy and anonymity, but it still left some traces that could be used for forensic investigation. In short, experiment A shows no protection. IP and DNS are exposed. Experiment B shows better protection. IP is hidden and DNS is encrypted, but browser fingerprints still remain. Next, let Guoli introduce experiment C and compare the results.
Now, let me focus on experiment C, Tor identity engine check. We used the Tor browser on a Windows 10 VM and captured traffic with Wireshark. The first test was IP masking. Traffic extended way of the Sweden, Romania, and so on. Our real senior IP stated hidden. The second test was DNS and WebRTC protection. DNS went through Swedish servers with no local NICs. WebRTC showed no IP exposure. The third test was traffic encryption. Wireshark saw DNS 1.3 end-to-end, no plaintext or SNN NICs. We see the two applicants and UTS education and AU worked fine. Identity and didn't bring normal browsing. Most importantly, the browser fingerprinting test. Baseline carries uniqueness was 99.98%, but Tor randomized it. Found dropped from 500 to under 200 of our three methods only Tor resistant fingerprinting well. Trade-off. Multi-hop is the latency, so it's slower than VPN and Baseline. Let's summarize the difference among the three methods through a comparison table. For public IP, Baseline shows the real senior IP. The VPN swaps it to a random extent. Tor hops across multi-countries. For DNS requests, Baseline sends plaintext to endpoint 8. VPN encrypts ESN the tunnel to 10.2.10.1. Tor encrypts through either relays. WebRTC NICs extended in Baseline, where both VPN and Tor successfully prevented some. Carries fingerprints were 98%. Unique in both Baseline and VPN, but Tor successfully randomed some. Found detection followed a similar pattern. Baseline and VPN detected over 500 phones, where Tor limited it to less than 200. For traffic encryption, Baseline only had HTTPS encryption with visible SNN fields. VPN prevented for tunnel encryption, while Tor offered multi-layer TLS version 1.3 encryption, which is the strongest. For speed, Baseline was fastest, VPN medium, and Tor slowest. Identity hidden level was exactly opposite. Baseline low, VPN medium, and Tor highest. The key insight is while VPN only protects the network layer without chatting browser or hardware fingerprints, while Tor is the only solution that actively uses fingerprinting technology to hinders well. But usage trends still show up. The folders place circlet state pre-fails JS and Windows notch logs prefetch, and even the 4688 new skills. Even deleted state may live in volume central copies or unallocated space. On the network, you will see context to dictionary servers on channel 1, necessary, and OCL 9151. That state will flag them. Memory dumps will circuit recent only sense and configure. Volatility 3 and bulk structure handles that. Investigator stage 6 into a timeline against the suspect activity. And remember, using Tor and algorithm only open circuit mistakes There are session to illegal acts. Net production ramp from baseline VPN core, but forensic echoes remain.
Alright, thanks, Goli. And I will introduce network anonymity and privacy protection. The online privacy is more important than ever, but it also creates serious challenges for digital forensics. To explore this topic, we test three environments. First one, the baseline, the normal connection without protection. Number two, VPN, using the Porton VPN. Number three, the tiered network, the most anomalous but complex option. Our goal was to compare the IP masking, the DNS leakage, and forensic trace across the setups. We used the tools like Wireshark, the browser leaks, a DNS leak test, and VirtualBox for experiments. Second one, the experiment result summary. Here is a quick comparison of our findings. In the baseline case, everything was exposed. The real IP, the DNS request, and the browser fingerprints showed 99.98% uniqueness. With the VPN, our IP was masked, DNS was encrypted, and WebRTC leaks were blocked, but fingerprints remained the same. Tor gave the strongest anonymity. IP changed constantly. The DNS was protected, and browser fingerprints were randomized. However, there's a trade-off. The baseline is fastest, VPN is balanced, and Tor is the slowest but most secure. Also, forensic traces vary. Baseline leaves many, VPN leaves some. The Tor leaves the least, but not zero. The key recommendations. We create practical suggestions for three types of users. First one, for user, VPN with DNS, leak protection, disable WebRTC, and if possible, use Tor in safest model. Second one, for investigators, look into system-level evidence, like registry artifacts, memory traces, and network behavior. The third one, for organizations, the monitor DNS logs, block Tor via no exit no list, and restrict all authorized apps with the app locker. These layered defenses can help both protect privacy and support digital investigations when needed. The final insights. Here are our key conclusions. First one, the VPN and Tor both enhance privacy, but Tor offers the highest anonymity. The forensic strategies must move beyond just IP tracking. Endpoints and behavior analysis are essential. Most importantly, anonymity is layered. No tool is perfect alone. Even encrypted traffic leaves behind the metadata, such as timing, connection patterns, and user habits. The true privacy requires a mix of tools, careful habits, and awareness. All right, thank you for listening.